15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello, and thank you for joining us on Space Nuts. It's a show about astronomy and space science. I'm your host, Andrew Dunkley. It's great to have your company once again. And this week on episode 275, we're going to be answering audience questions. We've got a whole batch of questions in. We're going to mix up some audio questions and some email questions so that it's all fair. And we're going to be looking at gravitational waves and what happens when they hit a black hole. We've got questions about redshift, questions about ramjet travel, and a really good question asking Fred about some of the personal finds in astronomy that he's been excited about over his long career. So we'll be looking at that and plenty more today on Space Nuts. Speaking of the man himself, let's welcome Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. The long Fred Watson, as well as the long.
Yes. Can you just move that Zimmer frame out of shot?
Okay, it's going to be one of those days, is it?
It could be. I think it is every week, isn't it?
Yeah, most weeks, yeah.
All right. We might as well get straight down to business. And our first question comes from Sydney.
G'day, Fred and Andrew. Look forward to every new episode of Space Nuts each week. Long may it continue. Paul from Sydney. I'm aware that black holes distort space-time so that matter crossing the event horizon can't emerge on the other side, as it were. Gravitational waves, as I understand it, are ripples in space-time itself. So what happens when a gravitational wave, or waves, confront the event horizon of a black hole? Does the ripple stop, then distorted? I'd be fascinated to hear your thoughts on that. Thanks, and keep up the good work. Cheers.
Is it good work? That is another question. But yeah, thank you, Paul. Great to hear from you, and hope all is well in Sydney. Well, Fred should be able to answer that because he's there.
It's pretty good, yeah.
He could have just come over to your place and asked. Oh, no, he couldn't. But anyway, gravitational waves and what happens when they hit a black hole. I suppose we should first review what a gravitational wave is for the sake of the exercise.
Yes, indeed, we should. And so given that Einstein's general theory of relativity back in 1915 demonstrated, postulated, but it was then proven to be correct, that space is flexible. Then if it's flexible, then you should be able to get waves passing through it. Waves in space-time, in fact, because it's space and time are part of the same entity. So the flexibility of space is really... we would call it totally rigid. I wrote the number down for spacewalk because I talk about this in the new kids book. And so I can remember what it is. Space is 100 billion times more rigid than steel.
Yes, I remember we did talk about that once.
It's a
tough
phenomenal
stuff.
number, yeah. So it takes a lot to bend it, but in the same way as if you hit a lump of steel with a hammer, it'll ring because waves are traveling through it. That's true with space as well. So if you've got an acceleration of a pair of neutron stars colliding or something like that, something accelerating, it sets up these gravitational waves which then pass through space and can now be detected by a number of detectors on our planet. But I think it's fair to say that the study of gravitational waves is in its infancy. It's only 5 years since we observed the first one. Yeah. 6 it might be now, and that means it's really still a study that is evolving, and it's evolving very rapidly. And so the interaction of gravitational waves with other celestial objects, whilst it's fairly well understood from a theoretical physics point of view, hasn't been that well studied because we haven't had the opportunity to do that. So the interaction of gravitational waves with a black hole, as I understand it, the theoreticians say that since a black hole has essentially zero cross-sectional area, the effect of it on passing gravitational waves is minuscule.
Ah.
In terms of
black holes are so tough. Not many things can tangle with them and come out on top.
That's right, indeed, that's right. Although gravitational waves kind of underlie what black holes are. In my naive, I'm not a theoretical physicist, but I do see what the sorts of things that they're saying. I would expect gravitational waves to be effectively refracted around black holes because they're a bit like electromagnetic waves are. So the bottom line is that they follow. I think they do. I think they are refracted. I'm just looking at web pages of my much more learned colleagues than me, and it says exactly what I just said.
Oh, there you are.
A gravitational wave follows a path through space-time called a null geodesic. This is the same path that will be followed by a light ray traveling in the same direction, and gravitational waves are affected by black holes in the same ways that light rays are. So they are distorted by it because because of the gravitational field distorts the space around it. It behaves like a gravitational lens, and that's the way it works. There's a caveat from this pundit.
There's always a caveat when it comes to astronomy. We know this, but...
Yes. Okay. All right. So all it's saying is that there's no transfer of energy between the gravitational wave and the black hole.
Mm-hmm.
So black holes gravitational waves behave like light waves.
Okay, which means that if we on Earth got hit by a gravitational wave right now, we'd notice nothing. We'd be able to detect it with our observations, but we wouldn't see or feel or know anything about it.
There wouldn't be an energy transfer except the minuscule amount that goes into making these mirrors vibrate in the LIGO and Virgo detectors.
Mm. So pretty simple in the end, Paul. It's not going to do much to a black hole, except the one in Calcutta, perhaps. But anyway, it's easily answered, as it turns out.
Well, it is when you know the right people to look it up with.
Yeah, of course, as you said, we still are learning about gravitational waves. So there might be other things that we haven't figured out yet that will turn up down the track. Thanks for your question, Paul. Appreciate it. Let's go to a text question. This one only came in this week, but it sort of caught our eye from Todd. He says, I read an article in a magazine, then searched the internet to find an actual explanation. Nothing. What is the actual mechanism by which expanding space causes redshift? I've read that it's to do with the change in the energy state of light, but what mechanism affects the light in this way? Everyone is simply asserting that this is a thing. I suppose it's possible we don't know the why yet. So thank you, Todd. That particular question certainly intrigued Fred, and he's going to answer it on the fly because I didn't tell him it was coming.
So it's true that it is a loss of energy, but a better way of thinking about it is if you regard light as a wave motion. Now, light has the property that it's both. It's both a wave and a particle. It has attributes of both a massless particle and a wave, and the particles are what we call photons. So probably the best way to think of it, and I think this is the way most physicists think of it, and it's really more to do with geometry, is that as light passes through an expanding space-time, as a wave motion, its wavelength is simply stretched. As space expands, so does the length of the wave, and so you get the redshift because an expansion of a wave or an elongation of a light wave produces a shift towards the red end of the spectrum. Then that's the sort of geometrical idea of what's happening, and that seems pretty reasonable to me. I've gone deeply into this, I have to say, and there is some very deep physics in the mechanics of space-time and what exactly it is. We don't really understand fully, but however, the naive version, if I can put it that way, is that as space expands, the wavelength of the light expands too. Now, because light is both a wave and a particle, the equivalent of the light wave getting longer in wavelength is that the particle has a lower energy. So photons, their energy, we normally with light talk about wavelength, but you could equally well talk about the energy of a photon. And as the wavelength gets longer, the energy decreases. So it's what happens. Another way of thinking about this is when light leaves an object like a dense star, for example, a neutron star, that light is losing energy because of the gravitational pull of the neutron star, and it doesn't slow down. It goes at the same speed, but it loses energy. It becomes redshifted, which is what we call the gravitational redshift. So once again, I think it helps if you think in terms of particles and waves. I hope that explains it.
I hope so too. Yeah. I'm not surprised that he had trouble finding answers on the interwebs, because they tend to steer you into all strange places. And you often end up in those forums where someone asks a question and there are 5,000 responses, none of which answer it.
Yes, that's right.
I hate getting hauled into forums. I find them so useless.
It's just like Space Nuts, really, isn't it?
It's very much like
5,000 answers, not of which are any use.
While we're talking about light, and I probably could have asked this question after the question on ramjets in terms of space travel, but they're kind of related to both. And I've been trying to think of a good time to ask you this question, so I hope you don't mind if I throw one in at a left field. We talk about light sails, using light sails and projecting spacecraft using light sails and lasers. And it got me to wondering if you could create a spaceship that uses light sails but propels itself with an onboard laser. Would that be possible?
Yeah, that's a really interesting question.
My sci-fi brain came up with that one.
Yeah, I like that.
So rather than have the laser on Earth firing its light into space and pushing along a spacecraft through the light sails, could you actually create a spacecraft that had an onboard laser to push itself along?
The problem is you're sort of picking yourself up by your own bootlaces.
That's what I wondered.
And I think that is equally true with light as it is with bootlaces. But
in fact, the laser being on board the craft is emitting the light. Therefore, it's not on board the craft anymore, and it's hitting the sails.
Yeah.
Could it work?
I mean, if you think of it, this is kind of the wrong way to think of what's happening here, because light is massless. But if you imagine it, that light's a stream of pellets, you're shooting them out with a laser, and that gives you a backward reaction on the laser. Then you're hitting the sail, and that gives you a forward reaction on the sail. So you are picking yourself up by your own bootlaces. And certainly all the light sail discussions I've seen involve effectively stationary lasers, usually in orbit around the Earth rather than on the Earth, because you want to minimise atmospheric absorption and things of that sort. So I think the answer is that no, you can't do it that way, because it's picking yourself.
The only way to do it for long haul travel would be to fire a laser from Earth, and you just go in a straight line, and when you get there, you smash into something because you can't stop. Or you could set up over time laser space stations.
Way stations, yeah. But you've got to put them there first of all, which means you've got to do the trip
the slow way.
Somehow, yeah. So you know, yeah. I think doing it from Earth's probably the way to go.
Yeah. at this stage. All right, fair enough. I just wondered. It got me thinking. Okay, thanks to Paul and Todd for their questions. We're going to take a little break, and when we come back, we'll have a couple of more audience questions for you here on Space Nuts with Andrew Dunkley and Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Thanks for joining us. We are doing audience questions on Space Nuts this week, and this one comes from, he's becoming a bit of a regular.
Hello, Space Nuts. Martin Berman Gorvine here, writer extraordinaire in genres galore. And let me just emphasize, this is my 3rd time around with you guys, and it's Martin, not Mark. My name is Martin Berman Gorvine. So my question this week has to do with the practicalities of travel out of the solar system using a Bussard ramjet. Once you hit the Kuiper belt and then the Oort cloud, won't the spacecraft be endangered by however much stuff is spread around out there? And if so, could the spacecraft dodge it by going out of the plane of the ecliptic? Or do the Kuiper belt and Oort cloud actually form spherical shells around the solar system? Love you guys. Can't wait to hear your answer. Bye.
Thank you, Martin. My apologies. I'm pretty sure it was me that called you Mark, and that would have been just my brain snapping at that particular moment. Probably got hit by a gravitational wave. But yes, Martin, I do apologise. Maybe if we get 4 or 5 more questions from you, I'll get it right.
Well,
ramjets.
Yeah, so just on that topic, Dave, you often used to get your name mixed up.
Yeah.
Fred and Dave.
Yeah.
Okay, let's start with what's a Bussard ramjet. And it's basically, and we have to preface this by saying this is entirely theoretical. It's a theoretical method to propel spacecraft that was actually proposed 60 years ago, back in 1960, 61 years ago, by a physicist, Robert Bussard. And then, it was grabbed onto by science fiction authors and science non-fiction authors, but mostly science fiction authors, and is kind of entered what you might call the popular scientific mentality. So what is it? The idea is that you build a device that has these excuse me, huge electromagnetic fields that spread thousands of kilometers into space on either side of the spacecraft, and you shape them into being like a scoop for the interstellar or interplanetary medium. Actually, the interstellar medium is what's usually considered. That's the hydrogen between the stars. So you're moving at high speed with this thing. You've got this gigantic electromagnetic scoop at the front. It scoops up the hydrogen and compresses it, just in the way a ramjet does with the air, a conventional ramjet burning fuel in highly pressurized air because of the forward speed of the device. So you've got the same sort of thing. You compress the hydrogen. You don't burn it, though. As you compress it, its temperature goes up, and eventually you get thermonuclear fusion, which is what happens inside the sun. And then, because of the magnetic field, you blast out the energy as an exhaust. The plasma that's created by the nuclear fusion, you blast it out as an exhaust, and it generates a thrust. So that is the basic idea of the Bussard ramjet, and it's actually, people have debated it over the 60 years since it was proposed as to whether it's feasible or not. There was some work done in later on in the 1960s that suggested that the hydrogen density in the environments of the solar system is just not high enough to make this idea work.
Okay.
Other people have suggested that you could use a different nuclear fusion chain, something called the CNO cycle, which is another way of building up atoms inside a fusion reactor to give you the effect. But I think the general view of the scientific community is, nice idea. So let's just step back, though, to get to... it's Martin, isn't it? Not Mark.
Yes.
Sorry, Dave, I forgot there for a minute.
That's okay, Frank.
To get back to Martin's question, is the density? Basically, the question is: would the density of objects in the Kuiper belt and the Oort cloud, would that be high enough to form essentially a problem for a thing with a scoop thousands of kilometers in diameter, an electromagnetic scoop? And the answer is no. The density of objects is very low out there. And, Martin's right that the Oort cloud is envisaged as a spherical shell of cometary nuclei. But if you add up all these cometary nuclei to get the mass of the Oort cloud, it is tiny. It's absolutely tiny. And that's telling you that the space between these things is enormous. The surface density is very, very low. So if you could get your Bussard ramjet to work, there's a good chance that it would speed through the Oort cloud without noticing a thing.
There you are. Of course, they are working on ramjets in our atmosphere that, as you said, operate with compressed air.
Yeah.
From what I hear, they've got potential to be rather fast, like Mach 6.
Yeah, well, you've got to get them to that sort of speed for them to work at all.
Yeah.
Which is something I didn't know when I was about 11, and I made one and tried to make it go by throwing it in the air as hard as I could. And I used kerosene, and I shouldn't tell people this because it's probably illegal now, in a small tube. It was only about 150 millimeters, 6 inches long. But it did get, because of the breeze of the air going past it, there was a fairly impressive flame came out of the back, but it certainly wasn't a thrust.
A friend of mine and I tried to make a jet engine once, and we did the turbines, the whole bit. We had it in a casing. We had everything set, and we fueled it with motor mower petrol,
great. Yeah,
which we gravity fed into it. We spun the turbines, lit her up, and it actually did slide across the floor for a bit until it exploded because of the petrol on top. Yeah, we didn't quite think about that.
No.
Yes. Yeah, you wouldn't do that in your garage these days, I wouldn't think. But, gee, it was fun. It's a lot of fun.
I have seen, sorry, we're way off track here, but I saw, it was my son, one of my sons directed me to a YouTube video several years ago in which somebody actually managed to make a gas turbine work based on a turbo compressor from a car, an old turbo compressor, which actually has the main components. It's got a turbine and a compressor, and all you've got to do is connect them up in the right way and squirt fuel in and get it going at high enough speed, and sure enough, it'll work.
Yeah,
it's impressive. Yeah,
don't try this at home.
No, it looked like a total fire risk,
and I'm not joking.
Everything got red hot, by the way. That was the thing. You can see it all glowing.
Yeah, well, we got red hot tempers fired at us.
Yeah, I bet you did.
Yes. All right. Thank you, Martin. Great to hear from you. Now we're off to Germany.
Hey, guys. This is Gloomy from Germany. I'm a frequent listener. I really love the show, and thank you very much for the great work you're doing. So I was just wondering, since you've been in the field for such a long time, for a long time, yeah? You've been around for a while. I was just wondering, like, a lot of things have come to light over the last couple of decades, and many of those have reshaped the way how we view the universe quite dramatically. I was just wondering if you would be willing to share one or two examples where such discoveries have kind of come close to you, have been personal to you, maybe because you had to reshape your views in a big way, or because something really, really unexpected came to light, or I don't know, for any other reason. Just maybe one or two prime examples of the most personally exciting discoveries that have come to light while you have been in the field. Yeah, that would be cool if you could share that. Thanks a lot for that. And yeah, as I said, Kate, a great show. Keep up the good work. And thank you very much for it.
Thank you. I think you said Gilmy. Could have been Mark. I'm not sure. But yeah, lovely to hear from you, and refer to previous comment about Zimmer frame. Yes, a couple of personal discoveries that you found personally exhilarating. I think, if I may go first, because I'll be very quick, for me it was once watching a documentary, and even though I knew it, it wasn't until they said it that it actually dawned on me that there was a time where people did not know that the sun was a star. And it kind of gobsmacked me, and it stuck with me. But it was. I think that the fact was figured out quite some time ago, but for a long, long time, people didn't see the sun as being the same thing as all the other dots in the sky. And it was only sort of one day someone went, you know what I reckon? I reckon that's a star. And voila, the revelation was made. And that stunned me, that I never considered the possibility that at some stage in the history of humanity, we didn't put that together. And so I found that quite a revelation. And to me, that, even though I wasn't around, Fred might have been, 450 BC, I think it happened. The knowledge that we gained from that was quite incredible, and we still to this day study the sun and are learning more and more about it. And knowing that it's a star is something that we all take for granted. But for some time, we did not put the two together. So for me, that is I find that a very personal moment when I came to the realisation that people didn't know it was a star at some stage in the past, like a couple of weeks ago. But and I suppose the other thing for me growing up, I think the biggest thing that happened, which is not quite what you're asking, but for me was the Apollo missions and being able to sit there and watch someone step onto another world for the first time in human history. I still equate that to being one of the greatest achievements of humanity. And look where it's taken us now. And we did it so fast. That's what I think is extraordinary about the way we went from the first flight to the first step on the moon in such a short time frame. Incredible. So those are my couple of thoughts, Fred.
Yeah. And it's, I've sort of been involved with science since I was at school, and that's a long, long time.
Gilmy knows that.
Yeah, 60 years of being a scientist. It's a bit frightening, really. But the things that come to mind to answer a question like this are things that I certainly wasn't involved with the discoveries, but I was close to the action in that, in particular, when I was an astronomer working at the Royal Observatory in Edinburgh in the 1970s, I was actually working on our own galaxy and the motion of stars in the galaxy. But a lot of my colleagues were working on cosmology, the large-scale structure of the universe, how galaxies behave. And I remember very clearly when the first gravitationally lensed objects turned up, and in particular when people started discovering fragments of Einstein rings on images taken with large telescopes. This is before the Hubble telescope. It's it actually wasn't before the Anglo-Australian telescope. The Anglo-Australian telescope was working then, but it was certainly early in the piece, and people started seeing circular features on deep photographs of the sky. And I remember the discussions about what these could be. A lot of people quipped that, somebody had put a coffee cup down on the photograph and you got this circle mark on the image. people wondered whether they were spiral arms that had broken off galaxies or something like that. And then, the real pundits amongst them remembered that Einstein had predicted in 1916, I think it was, after the general theory had been published, that you might get circular features caused by the lensing effect of dense objects. The fact that gravitational lenses turn things that are a long way off in the universe, if the light from them goes past a massive object, then it gets turned into this distorted image. And sure enough, that's what they turned out to be. But it was so unexpected to me. I remember almost having my breath taken away at the time when this entirely new suite of phenomena was discovered. With over a very short time period, it sort of emerged from the back blocks of fairly obscure publications, and then suddenly we were in a regime where we could see gravitational lenses everywhere. And the other big change was throughout that 70s period, we were all pretty well fixated on the idea that the expansion of the universe would slow down, and eventually there might be a big crunch. I wrote a spoof paper on it once, which never got published, probably just as well. But they all thought that eventually the expanding universe would collapse on itself, and there'd be a big crunch, perhaps some billions of years down the track, which, of course, Brian Schmidt famously named the Gnab Gib for the Big Bang backwards. We've talked about that before. We didn't think of any of that at the time, but it was, it was sort of common knowledge in astrophysics that the universe would slow down in its expansion because of all the gravity of everything inside it. And so the 1998 discovery that Brian and his colleagues made, and Saul Pulamuta and his team in the USA, that the expansion of the universe is accelerating, that was just breathtaking. It blew us all away. It was the last thing we expected. By then I was working in Australia. I was the astronomer in charge at the National Observatory. But astonishing stuff. Yeah. Just going back to the idea of the question, it's been in my mind for a while that I'd really like to do a book on how astronomy has changed during my lifetime, during my time working in it, because it's transformed completely. And a lot of that's come from the technology that we have, the instrumentation that we use now.
You could call it, Fred Watson, a century of knowledge.
Century of ignorance.
Very good. Gilmy, I hope that covers what you are asking us to do, and I think Fred would have much, much more to offer if we gave him extra time. So maybe we can do that again in a future episode and talk about some of the other revelations that he's come across in his amazing career, like holding the tripod while Galileo set up his telescope, things like that. Just amazing. Man.
Me and Galileo were like that.
They were best buds. Yeah. All right.
His English was rubbish, though.
This is Space Nuts with Andrew Dunkley and Fred Watson.
Space Nuts.
By the way, if you would like to become a patron of Space Nuts, you can do that by logging onto our website. There are all sorts of options to maybe kick the can with a little bit of cash once a month if you so desire. It is totally optional, but you can do that by visiting spacenutspodcast.com. Click on the support Space Nuts button, and all the options are there so that you can support us through either Patreon or Supercast or PayPal or whatever you like. A bloke gave me cash the other day. Yeah. Under the table. But it's whatever way works for you, and we do appreciate the support. If you feel compelled to do that, great. If you don't, that's fine too. So go to our website if you'd like to become a patron and click on the Support Space Nuts button and go from there. Okay, Fred, we're off to Sweden.
Hello, Fred and Andrew. It's Simon here from Sweden. I've been listening since episode 3, I think, and I still love it, so keep it up. I've been wondering if it would be possible for an object large enough to be considered a moon to be caught in Earth's gravity and go into an orbit. In other words, would it be possible for us to get a second moon?
No, that's it. Okay, thank you, thank you, Simon. Great to hear from you. And the answer is yes. So see you next week. This does happen from time to time, and I've just picked up on an article, Fred, that said that Earth did pick up a second moon as recently as late last year. And it won't stay there because we can't hang on to it, and it's only a tiny little thing. But it has been kind of our second moon for a little while now. I'm not sure if it's left yet or if it's still rotating around the planet. But it would have been passing by. We've picked it up with our gravity. It's stuck around a bit and will eventually get flung off, I think.
And that's exactly the answer, Andrew. You've been doing Space Nuts for too long.
I know.
Yeah.
It's 2020 SO, this object that I happened across.
Okay. Well, the one I'm thinking of is 2020 CD3, which that was in orbit around the Earth between 2018 and 2020. Okay. What's happening is these near-Earth objects, near-Earth asteroids, basically, are in orbits that sort of intersect the Earth's orbit. They have some sort of resonance with the Earth's orbit, and they basically just get picked up by the Earth's gravity and becomes essentially a satellite of the Earth. Sorry about the banging. You probably hear
housework.
It's
housework getting done.
It's our new dishwasher being installed. Yeah, never mind. I'm glad I'm not doing it. That's all right. I don't have a hammer big enough to do that sort of thing. So yes, it's the Earth's gravity can things that are. I guess what we're saying is these objects are moving relatively slowly relative to the Earth and come near enough to the Earth that the Earth's gravity grabs them, and they become orbital around the Earth for a short period. And then the effect of the sun's gravity and probably the gravity of the other planets, as well as the interference from the moon, which is much bigger than any of these objects. They're all tiny lumps of rock, basically. It means that they're thrown off. There's one what's sometimes described as a stable quasi-satellite of the Earth. That's a thing called 469219 so let me get this right. Kamo'olawa. And that's a Hawaiian name, which means it was discovered probably by Pan-STARRS 2. Yeah. Kamo'olawa. Nearly right. That's an object that it's not a true satellite because it's too far away from the Earth, but it's a sort of quasi-satellite. So it orbits. It orbits around probably one of the stable Lagrange points of the Earth. That's the kind of what essentially happens, and that raises the prospect of what you might call Earth Trojans, which are asteroids that live in that area of space 60 in the Earth's orbit, but 60 degrees above, 60 degrees ahead of the Earth or 60 degrees behind the Earth, just like the Jupiter Trojans. Sorry, I'm mangling this answer, Andrew, probably partly because of the hammering. But the bottom line is, yes, things can be captured. Often these objects turn out to be spacecraft rocket bodies. They're often rocket bodies. In fact, a recent one was actually, I think, the launch vehicle for Chang'e 2, which was one of the early Chinese lunar missions. Can't remember when that was. Actually, 8th of December 2017. That's an object called YX205b9 in an orbit around the Earth, but actually is the booster stage from Chang'e 2.
But picking up something larger is very unlikely. Where it passes by like Oumuamua and Borisov, they'd be at the wrong angle, wrong speed,
actually.
Wrong place to actually get picked up. Yeah.
In fact, they're going too fast even to be picked up by the sun's gravity. So
so it's got to be the right place, the right speed, and then we might pick it up. But it doesn't ever seem to be a permanent pickup. It's it's something that, can't hang on and gets flung off again like this little rock that they found last year. Okay. There you have it. And thanks for your question, Simon, and I hope all is well for you in Sweden, yeah? Let us move, I don't even know if that's how you say it. Let us move on to our final question, and this is a text question that comes from Andrew. He said, I love the podcast. Well, that's one. That's good. Assuming mathematics is the same across the whole universe, where do you think it is stored? I assume not in our 3D plus time physical world. And do you think other intelligent life has found it in the same order as earthly humans? Wow, that's deep.
It's a great question. It's got echoes for me of where the laws of physics come from. Because, we understand the universe. We've got these physical principles that seem to hold for all scales, whether they're the centers of atoms or superclusters of galaxies. Physics seems to work until we've got these laws of physics that have been evolved. But where did they come from in terms of how the universe works? And I think this is one of the big mysteries. Now, those laws are highly mathematical. So the mathematics that we use to manipulate those laws is in itself an entity whose origin is not really known. And I think this is really a philosophical question. Where does mathematics live? Is there a massiverse or something like that? And I haven't really done much reading on these topics, but I'd like to, because I think it's really interesting stuff. But I do like the idea of, if you do have intelligent species elsewhere in the universe, would they discover mathematics kind of in the same order that we've done, going through basic arithmetic and kind of heading through calculus, and then things like Hilbert spaces, essentially abstract algebra, all the stuff that we know is useful when you describe quantum physics, things of that sort. Would that be the path that will be followed? And my guess is that it probably would be something like that, something like what we followed here on Earth. I
can't imagine that mathematics would differ regardless of where you were in the universe or who you were in the universe. The mathematics would have to be the same. It just wouldn't make sense for it to differ greatly. Otherwise, the universe wouldn't be the universe. I don't know. But you could envisage a situation where the mathematics that we use is like a small subset of the total mathematical content of the universe, and we're beavering away with our little bit, and there might be somebody else somewhere who's looking at a different bit of the of this overall structure of mathematics. I suppose it's also possible there are elements of mathematics that we haven't yet. Yes, that's what solved. I mean. That we've got a known mathematics, because the people are still doing research in mathematics. They're very, very clever people, maybe somewhere else there are different mathematical constructs. It's a really nice idea. I should think about that a bit more. I often, well, not often, but once in a while there'll be a news story pop up in journalism about the newest prime number that's been discovered. Yeah, and that's right. They're not easy to find. Not now, because the numbers are so incredibly large. And so they have supercomputers trying to calculate what the next prime number is. It's quite remarkable. But I would think across the board, mathematics is the same for humans as it is for Martians and Andromedans. Well, certainly, it works in the solar system the way it works here on Earth. Whether it works, on some galaxy at the other edge of the universe, other end of the universe, is a different matter. Indeed. But Andrew, love the question. Thanks for sending it in, and so good to hear from you. And thanks to everybody who contributed to the program this week. Don't forget, if you do have questions for us, you can send them via our website, spacenutspodcast.com. Click on the AMA link up the top, and that's where you can send us audio and text questions, or you can click on the thing on the right-hand side and record your voice message right there. It's really quite simple, and that's all there is to it. So spacenutspodcast.com, or you can go to spacenuts.io is the other URL if you prefer. They both take you to the same place. So, potato, potato. That brings us to the end. Fred, thank you so much. Great to catch up, and I hope that dishwasher turns out to be a real winner. Sounds like it's going in nice and solid.
We hope so too. Yeah. I think it's going to be part of the fabric of the house.
Yes, indeed.
Thanks.
Fred's universe.
Thanks very much, Andrew. We'll speak again soon.
Good to talk to you. Catch you soon. Fred Watson, astronomer at large, part of the team here at Space Nuts. And of course, we say thanks to Hugh back in the studio for doing whatever it is that Hugh does. And from me, Andrew Dunkley, thank you for joining us. Look forward to your company next week. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.